Hi guys, we're going to talk about Dalton's law of partial pressure. So Dalton said that if you have a mixture of different gases, then the total pressure of the mixture is going to equal to the sum of the partial pressures of the component. So P total is going to be equal to the partial pressure of the first gas plus the partial pressure of the second gas plus the partial pressure of the third gas, and so on. So pretty basic, right? Last year we talked about Dalton's law in honors chem, and it was a pretty easy concept. So for example, if I have air and I want to look at its pressure, the atmospheric pressure, well, air is made up of all kinds of gases, right? It's made up of nitrogen, argon, carbon dioxide, water vapor, and so the total pressure of the air is equal to the partial pressure caused by the nitrogen plus the partial pressure caused by the oxygen plus the partial pressure caused by the CO2 plus the partial pressure caused by any water vapor in the air, any argon, and so on, right? So we are going to use that, but expand a little bit more on it. So let's say that you have a mixture. In a mixture of gases, your components will all be at the same temperature and the same volume, right? So if I had a balloon that I fill with, some kind of gas mixture, this balloon has a certain volume, so that volume is taken by all the different particles here, and it also has to be at the same temperature, right? Like all the gases that are inside of the balloon have to be the same temperature. So let's write that down here. So in a mixture, the components, so the different gases that make up the mixture, will be at the same volume and temperature. So what does that mean? Remember when we talked about the variables for gases and the combined and the ideal gas law? Well, if we hold two components or two variables constant, then we can relate the other two. So remember, the other two were moles and pressure. So we can say that the pressure of substance A compared to the total pressure is equal to the moles of A over the total moles, right? So kind of like P1 over N1 equals P2 over N2, 1 being component A and 2 being the total. Right, so we can look at this relationship here, direct relationship between the pressure and the moles. Well, moles of A over total moles, that's the mole fraction, right? So we can write it as P, partial pressure of A over the total pressure, is equal to the mole fraction of A. We can rewrite this as partial pressure of A is equal to the mole fraction of A times the total. So this is kind of an equation that we're going to be using sometimes. You can use it in any of these forms that you would like, but that's how you can come up with it if you have a mixture of gases. So let's try a few problems here. So this one says, since fluorocarbons are no longer thought to be environmentally safe, chemists have had to derive substitutes. Two gases that have been used are propane and butane. And this is specifically isobutane. So suppose you mix a certain number of grams of propane with a certain number of grams of isobutane. The mixture is then forced into a can until the total pressure is 1.5 atm. We want to know what the partial pressure of each gas is. So we have this mixture, and we want to know, we have the total pressure, we want to know what is the partial pressure of each gas. So we can use this if we'd like. So we can say the partial pressure of the propane is equal to the mole fraction of propane times the total. And we can do the same thing for the butane. To find the mole fraction, remember you gotta convert everything to moles, so let's do that first. Let's find the moles first. So I'm gonna find moles of the propane. And so I have 22 grams of that. Grams on the bottom, moles on top. And 1 mole of propane is 44 grams. And so here I have, ooh, look at that. You can do this in your head, right? Half, right? 0.50 moles of the propane. Let's look at the isobutane. So we have 11 grams of the C4H10, 1 mole of butane is 58 grams. And so this gives us 0.189 moles of butane. I'm going to go ahead and add those two together so I can get the total. So 0.689 moles total. All right, so now I can use this here. So I'm going to calculate the partial pressure of the propane first. So it's going to be equal to the mole fraction of the propane times the total. And so it is equal to, my mole fraction would be moles of propane, so 0.500 moles over 0.689 moles. So that is my mole fraction times my total is 1.50 atm. And so I got my partial pressure of the propane to be 1.09 atm. If I wanted to find the mole fraction of the butane, I would do the same exact thing. So it's going to be the mole fraction of the butane times P total. So 0.189 moles over the total, 0.689. That gives me the mole fraction, and then times 1.50 atm. And this gives me 0.413 atm. What would have been an easier way to find the partial pressure of this if we already knew that? Well, we know that the total is 1.50 atm. We know that the total is equal to the partial pressure of this plus this. So you could have just subtracted. You could have done 1.50 atm minus 1.09 atm and gotten that. So you can always take shortcuts, you know, as long as you understand what you're doing. Okay, let's look at the next one. So the next one says, hydrogen gas can be produced in the lab by the oxidation of iron and an acid by the reaction given here. We want to assume we carried out the experiment and collected a certain volume of the hydrogen gas over water through displacement. The temperature of the gas mixture was 26 Celsius, and they give us the total pressure as well. And then they ask us a whole bunch of stuff. So let's talk about this first. When you are collecting a gas in the lab, typically you do this through water displacement somehow. So, you know, in this case, we have a reaction between iron and an acid. So one setup could have been, you have your reaction vessel here. And so you have, you know, your iron and your acid, and you stopper this. You use a stopper that has a hole in it. And then you take that tube and connect it to maybe some other vessel. Sorry, my drawing is not that great. usually a eudiometer or something like that in water. So this is water. And what you do is you get a eudiometer. A eudiometer is basically like a graduated cylinder that's inverted. So it's kind of like a glass tube. It looks kind of like a burette almost. And it has graduations usually. And you connect this, sorry, right there. So this also has water in it. So you invert it upside down in the tub of water. And what happens is as the reaction starts and you form a gas, so you see bubbles here, the bubbles start going up here through, and then they start bubbling here. And what happens is the water that's in your eudiometer gets displaced, and so this would be your gas. So in this case, the hydrogen gas, right, is going to collect here, and then this is water. So as you form more and more hydrogen gas, it builds up, and the water here, goes out into your beaker or tub of water. And then you can measure the volume of this. Usually a eudiometer, like I said, is kind of like an inverted graduated cylinder, so you can measure the volume here. And you can find the volume of your gas. Now, what happens though is that if you collect a gas through water displacement, which usually is the method that we use in chemistry typically when we collect a gas, what happens is, because this was filled originally with water, remember at the surface of any liquid, there are some vapor particles. There are some gaseous particles of that vapor. So there are some water vapor particles that are trapped here as well. And so this is not just hydrogen, but it is a mixture of hydrogen and water vapor. So when you're collecting a gas over water, you will always have that gas plus some water vapor as well. It's a mixture. Okay. And so the pressure that we measure, they tell us that the pressure was 745 millimeters of mercury. That is the atmospheric pressure, because this is open, so the pressure here is going to equal to the atmospheric pressure. Or even if we measure the pressure that's just here as opposed to atmospheric pressure, that is the pressure that is caused by both gases. So that is the total pressure. So then how do we know what the pressure is of just the hydrogen? Well, if you look at the chart that's at the top of the table here, this tells us the water vapor partial pressure at any given temperature. So at these temperatures, these are the partial pressures of water vapor. Remember that the higher our temperature is, the higher the partial pressure of the gas, right? Because the higher the temperature, that means that if you have a liquid here and the particles are moving faster, more of those particles are going to escape as a gas at the surface and collide together and cause a higher vapor pressure. So the higher the temperature you see, the higher the vapor pressure. And these pressures are given in torr. Remember that a torr and a millimeter of mercury are equivalent. So if we look back at our experiment and we see that it's at 26 degrees, and we look at 26 degrees Celsius, there is our vapor pressure of the water vapor. So this is the pressure that's caused by just the water vapor, and so the rest of the total pressure is caused by your gas. Okay, so let's see how we're going to use this in our calculation. So first of all, it tells me how many total moles of gas were in the container. So if I want to answer letter A, let's see, I want moles of gas. I'm given the pressure, I'm given the temperature, I'm given the volume, so I could just use a PV equals nRT. And every time I write PV equals nRT, I always write what gas I'm doing this for. So in this case, I'm doing it for the total mixture, meaning H2 and H2O gases together. So that means I need the total pressure, total volume, total moles is what I'm getting, and total temperature, right? Which I guess the same thing as just temperature. So total pressure is given to us. It's 745 millimeters of mercury. The total volume, that tells us it's half a liter. And we're going to get N total. R obviously is going to be the same. Since we're using millimeters of mercury, I want to use the 62.4 millimeters of mercury times liters per mole Kelvin. And then my temperature is 26 Celsius, which is 299 Kelvin. You always want to use kelvins when you're doing gas calculations. So the N total ends up being, you solve for N, you get 0.200 moles. And that's total. All right, we got A. Next, we want to know how many moles of hydrogen did we prepare. So we don't want the total, we just want moles of hydrogen. So we could do a PV equals nRT for hydrogen. All right, so let's do that. So just hydrogen. So I want the pressure of just hydrogen, not the total pressure, right? So I know that P total is equal to the partial pressure of the hydrogen plus the partial pressure of the water vapor. I know that the P total is 745 millimeters of mercury. I'm looking for the partial pressure of the hydrogen. And I know that the partial pressure of the water at 26 Celsius is equal to 25.21 torr or millimeters of mercury. So this number would have to be given to you on the test if you are collecting a gas over water. So 25.21 is the partial pressure of the water. And so I know that I can get the partial pressure of just the hydrogen by subtracting those two numbers together, and that gives us 719.8 millimeters of mercury. And I'll round at the very end. So back to PV equals nRT, the partial pressure of just the hydrogen is 719.8 millimeters of mercury. The volume, well, the hydrogen gas takes the whole volume of the container, just like the water vapor takes the whole volume of the container. Remember, these are tiny particles in a large container. They fill to the volume of the container, so it is still 0.500 liters. Now I'm solving for the moles of just the hydrogen. R is still 62.4 millimeters of mercury times liters per mole Kelvin. And my temperature is still 299 Kelvin. And I get, and for just hydrogen, from this calculation, I got 0.0193 moles of just hydrogen. Okay. Part C says how many grams of iron were required for this reaction. So, I got moles of hydrogen. What do I do? Well, I could balance my equation and do some stoichiometry, right? So let's balance this here. You'd need 2. So my hydrogens are good, irons are good, even the charge is good, right? This is a total of +2, this is a total of +2, so that's how you balance it. So let's do part C. We know that we need 0.0193 moles, or produced, I'm sorry, not need. We produced 0.0193 moles of hydrogen. We can use our molar ratio to get moles of iron, so 1 mole of H2 for every 1 mole of Fe. And I got that from my molar ratio here. And it's asking for grams, so I'm going to go from moles of Fe, 2 grams of Fe. Molar mass of iron is 55.85 per mole. and this gives me 1.08 grams of Fe. All right, let's try one more problem. So it's asking me, what will the partial pressure and mole fraction of each gas be when mixed at 20 Celsius? And they show us a diagram. It looks like we have two vessels here that are closed off from each other. And in one vessel I have hydrogen gas, and I have a liter of that, and I'm given the partial pressure of it. And in the other side I have nitrogen, and I have half a liter of it at 338 millimeters of mercury there. So I have the volume and the pressures for both of them. So they tell us we're going to mix them. So basically I'm going to open this up right here, and I'm going to let the two of them mix together. So I'm going to open this up right here, and they're going to both mix. So the question is, what will the new partial pressures be, and what will the mole fractions of each gas be? There's actually two ways to do this problem. So the first way is maybe we can use PV equals nRT for each of them separately to get the moles first. And then I can get the mole fraction, and then I can say that the partial pressure of each of the gases is equal to the mole fraction times the total, right? So I could do P of H2 is the mole fraction of H2 times the total, and I could do the same thing for N2. So let's do that. So we're going to start with the moles of each, and we're going to get that from PV equals nRT. So I'm going to do PV equals nRT for hydrogen. And my partial pressure of the moles are not going to change whether they're mixed or not, right? And so if I get the moles of it, of the hydrogen just by itself when it was closed off, it's going to still be the same as the moles when they're mixed. So I'm going to say 475 millimeters of mercury. The volume is 1 liter. So again, this is just when they're closed off. 1 liter. That's going to be the moles of the hydrogen times 62.4 millimeters of mercury times liters per mole Kelvin. And my temperature, they tell us we're at 20 Celsius, which is 293 Kelvin. And I got my moles of hydrogen to be, let's see, I got 0.02598 moles. Again, I'll look at sig figs, at the very end here. I'm going to do the same thing for the nitrogen. PV equals nRT for nitrogen this time. And so, again, just with it closed here, I have the 338 millimeters of mercury, and that was in half a liter. R obviously still the same. And then my temperature is also the same. So this is going to give me the moles of just the N2, and I got 0.00924 moles of nitrogen. Okay, so that's when they were separate. Now I'm going to go ahead and open it up. My moles are going to be the same, right? I'm going to go ahead and calculate the total moles as well. And total is 0.02598 moles of hydrogen plus 0.00924 moles of nitrogen. So my total moles are going to be 0.0352 moles. All right, so now I'm going to, you can calculate your mole fraction, or you can separately and then plug it in, or you can go ahead and do your equation here, but we're going to say that the partial pressure of the hydrogen is, oh, sorry, we need the mole fraction. So let me go ahead and calculate the mole fraction as well. I'll do that first and then I'll plug it in. So my mole fraction of the hydrogen is going to be the moles of hydrogen, so 0.02598 moles of H2 over the total, which we got to be 0.0352 moles total. I got 0.738. So that's one of my answers. I'm going to do the same thing for the nitrogen. So it's going to be the moles of nitrogen, 0.00924 moles of N2 divided by the total, 0.0352 moles total. And this gives me 0.262. Now, I didn't have to do this, right? I could have said, well, the mole fraction of the H2 plus the mole fraction of N2 should equal to 1, right? You add them up together, you get 100%, which is 1. So I could have just said the mole fraction of N2 is 1 minus 0.738. And that would have given me 0.262. So I could do that as well. You can always take shortcuts as long as you know what you're doing. Now I need to find, I got the mole fractions, now I need to find the partial pressures. So I'm going to say the partial pressure of H2 is equal to, oh, I'm sorry, I wrote it backwards. There we go. Partial pressure of H2 is equal to the mole fraction of H2 times the total. So I have the partial pressure of the mole fraction of the H2, got it right here, but I don't know what the total pressure is. Can I add these two and that would give me the total pressure? The answer is no, I cannot. Why? The total pressure in reality, when I open this up here, is going to be less than these two combined together. Why is that? Because remember, pressure is related to volume, right? And so this hydrogen is under this pressure, this nitrogen is under this pressure in these volumes. When I open this up, the hydrogen has 1.5 liters to move in. So it's going to have less pressure. Same thing with the nitrogen. The nitrogen is going to have 1.5 liters to move in instead of half a liter. And so since both of them are going to be opened up and will occupy a bigger volume, they're each going to have a smaller partial pressure. What I need to do is to actually calculate what the new total pressure would be. And so I could do a PV equals nRT for that. So I'm going to do a PV equals nRT for the total after mixing. So P is what I'm solving for. V, now that I open this, I'd have 1.5 liters. So 1.5 liters. N is the total, right? So both of them together, so I can use my total N because I got it here. 0.0352 moles total. R is 62.4 millimeters of mercury times liters per mole Kelvin. And my temperature is still 293 Kelvin. And I get P total to be, should be a number less than those two combined. I got P total to be 429 millimeters of mercury. So now I can use this in here. So my partial pressure of the hydrogen is 0.738 and my total pressure is 429 millimeters of mercury. And so this partial pressure of hydrogen is going to be equal to 317 millimeters of mercury. For the nitrogen, I could do the same exact thing. So I could do partial pressure of the nitrogen is equal to mole fraction of the nitrogen times P total. So 0.262 times 429 millimeters of mercury. And so that ends up being 112 millimeters of mercury. And actually with sig figs for the nitrogen, probably need just 2 sig figs because of the 0.50, but it's not a big deal. Remember, it's plus or minus 1 sig fig. What's another way I could have done this instead of this calculation? Well, I could have said, well, the total is 429, hydrogen is 317, so I can subtract those two to get the partial pressure of the nitrogen. So this was a really long problem, but I think it's pretty cool. If you can do this, you really understand what's going on. There is another way to do this, though. Let's look at the other way to do it. It's actually maybe a tiny bit shorter. So the other way to do it is to think of it as with a combined gas law, like a P1V1 over N1T1 problem, right? You're changing conditions, right? So if I am changing conditions, I could say P1V1 over N1T1 equals P2V2 over N2T2. My moles are going to stay the same. My temperature stays the same, so it's actually a Boyle's law problem. P1V1 is equal to P2V2. So I could do that for the hydrogen to figure out what the new partial pressure is, right? Because I have the initial partial pressure, the initial volume. When I open this up, I change my volume to make it 1.5, so I can solve for what P2 is, and I can do that same thing for nitrogen. Isn't that cool? So let's do that. Let's do it the other way here. So I'm going to do P1V1 equals P2V2 for hydrogen first. So my initial pressure of hydrogen was 475 millimeters of mercury, and that was in 1 liter. I'm going to solve for the P2 when it's now 1.5 liters. And my partial pressure for the hydrogen is going to be, guess what, 317 millimeters of mercury, which is what we got here. Let's do the same thing for nitrogen. P1V1 equals P2V2, this time for nitrogen. So nitrogen originally was 338 millimeters of mercury, and that was in 0.5 liter. I'm going to look for what the new pressure is in 1.5 liters when I open it up. And my new partial pressure for the nitrogen is 112 millimeters of mercury. Right, matches here. Great. We're halfway done, right? Because we were asked for both the partial pressure but also the mole fraction. So now we need to find the mole fraction. So for the mole fraction, what you need to do is you could say that the partial pressure of the hydrogen is equal to the mole fraction of the hydrogen times P total, right? The partial pressure of the hydrogen was 317 millimeters of mercury, we found out. We need to find the mole fraction of hydrogen. What about P total? Well, these are the new pressures, right? So if I add those up, that's going to give me P total, which is 429 millimeters of mercury. So I can plug that here. 429 millimeters of mercury, and solve for the mole fraction of the hydrogen. It ends up being 0.738. No units for it. We'll do the same thing, or you could just say the mole fraction of nitrogen is 1 minus that. But if you wanted to show the calculation, you're welcome to. There's no need, but you can if you want. So this partial pressure is 112 mole fraction times 429 millimeters of mercury is my total. And my mole fraction of nitrogen ends up being 0.262. So a little bit shorter method, but both are equally correct, and both are really, really cool. It's a really good problem.